In this course, you'll learn how to apply machine learning to solve problems that are difficult, and some might say impossible to solve with standard coding techniques. This first module will provide some basic information about machine learning. This includes examples of machine learning, a definition of machine learning, and importantly, how machine learning differs from traditional programming. We will go over the two basic types of machine learning, supervised and unsupervised. We will see each of these types in action, which will clarify how they differ and when each type of machine learning should be used. After that, we will review the content of this course and the skills you need and the skills you do not need for this course. We will then have a brief discussion of how machine learning fits into the larger subject of data science. There's also a section on programming in Python and using the Jupyter Notebook environment we will use in the demos. Machine learning is one of those technologies that is all around us and we may not even realize it. For example, machine learning is used to solve problems like determining if an email is spam, how cars can drive themselves, and what products a person is likely to buy. Every day you see these types of machine learning solutions in action. When you open your email and your messages are automatically scanned, classified as spam, and moved to your spam folder. For the past few years, Google, Tesla, and others have been building self-drive systems that will soon augment or replace the human driver. And data giants like Google and Amazon have been able to use your search history to predict which items you're looking to buy and ensure you see ads for those items on each and every web page you visit. All of this useful and sometimes annoying and creepy behavior is the result of machine learning. But before we proceed, what do you think of when you hear the term machine learning? Perhaps something like this? While the thinking robots we see in movies likely use machine learning, defining the complex logic that lets the robots think is unfortunately beyond the scope of this course. So let's define machine learning in general and the specific type of machine learning this course focuses on. For this course, we'll define machine learning to be building a model from example inputs to make data-driven predictions versus strictly following static program instructions. This definition points out the key feature of machine learning, namely that the system learns how to solve the problem from example data rather than you writing specific logic. This is a significant departure from how most programming is done. In more traditional programming, we carefully analyze the problem and write code. This code reads in data and uses its control logic to determine the correct parts to execute, which then produces the correct result. With traditional programming, we use constructs such as if statements, case statements, and control loops implemented with while and until statements. Each of these statements has tests that have to be defined, and the changing data typical of machine learning problems can make defining these tests very difficult. In contrast with machine learning, we do not write this logic that produces the results. Instead, we gather the data we need and modify its format into a form which machine learning can use. We then pass this data to an algorithm. The algorithm analyzes the data and creates a model which implements the solution to solve the problem based on the data. Machine learning algorithms learn from data by utilizing one of two techniques, supervised or unsupervised machine learning. While this course is focused on supervised machine learning, it is important to understand the difference between the two techniques and when you would use one versus the other. In supervised machine learning, the subject of this course, each row of data has fields containing feature values and the value we want the algorithm to predict. For example, let's assume we want an algorithm to predict house prices. To accomplish this, we would pass a set of training data with each row of data containing features of the house such as its size, number of bedrooms, and the year the house was built, and the value we want to predict, namely the price. We pass many rows of this training data to the algorithm. The algorithm analyzes the features and the resultant price. It determines the relationship between the features and the price and creates a model that is trained to predict the price of the house based on the features. Then when the trained model is presented with data for a new house, it executes its logic and accurately predicts the price of the new house. Let's contrast this to unsupervised machine learning. In unsupervised learning, we are looking for clusters of like data. The algorithm analyzes input data and identifies groups of data that share the same traits. For example, let's start with a recording of a room full of people talking. We can convert this recording into data containing values of vocal attributes such as pitch, intonation, and inflection. We can then pass this mixed voice data to an unsupervised learning algorithm. The algorithm can analyze the voices and create a model that classifies clusters of data, words in this case, that have certain speech patterns of pitch, intonation, and other vocal features. This results in the ability to isolate an individual voice from the mixture of voices. Since it is important to understand the correct technique to use to solve a problem, let's recap the difference between supervised and unsupervised machine learning. A primary difference is what type of problem you're trying to solve. If you're trying to predict a value like the price of the house, then you're likely looking at a supervised machine learning problem. If you're going into a set of data and trying to find groups or clusters of like data, then this is likely an unsupervised machine learning problem. The data we have also matters. Supervised machine learning requires that we have some training data that has the value we are trying to predict. With unsupervised machine learning, we don't have the values, we are trying to figure out the values. As we saw in the examples, in supervised machine learning, we use the data with the value to train the model so it can predict values on new models like a new house. In contrast, with unsupervised machine learning, we get clusters of like data from the model. And importantly, in this course we'll cover supervised machine learning and not unsupervised machine learning. This choice was made because many of the machine problems you're likely to run into are predictions and are thus solved with supervised machine learning. Now let's take a few moments and go over the content of the course. We will start with an overview of the machine learning workflow. The workflow will provide the framework we'll use to approach our problem and ensure we do not forget any critical steps in developing a solution to the problem. Over the years, this framework has been followed to solve countless machine learning problems such as fraud detection, identifying spam email, and weather prediction. Once we understand the structure of the workflow, we will spend the majority of the course diving deep into each of the steps of the workflow. We will do this by applying the workflow steps to the sample problem of predicting if a person will develop diabetes. Diabetes is one of the leading causes of death in the world today. Up to 8.5% of the world's adults have diabetes. Prediction methods, like the one we are building, can help identify people at risk from this deadly disease. At the end of the course, we'll have a short review of what you have learned and where to go from here on your journey to learn more about machine learning. But before we go further, let's review the skills and experience you should have to get the most from this course. Let's start by discussing the skills I do not expect you to have. First, as the with Python in the title implies, we're going to be doing our programming in Python. However, you do not need to have any prior experience with Python. Throughout this course, we will learn by doing. That is, we will introduce the parts of Python as we use them, and in this course we will use version 3.5 of Python. We will use Jupyter Notebook as our development environment, and as with Python, you don't need to have prior experience with Jupyter Notebook. There's a quick getting started guide at the end of this introduction for those people who want to get a jump start on using Python within Jupyter Notebook. Finally, I do not expect you to have advanced math or statistics knowledge. While the algorithms are based on advanced math and statistics, we will be focused on using existing algorithms rather than creating new algorithms. Now let's take a look at the skills and experience you do need to have. First, you need to have some sort of programming experience. That can be in C, C#, VB, Java, or almost any programming language. The language specifics don't matter, but you need to be able to understand basic programming constructs such as assignment, conditional statements, loops, and passing parameters to functions. Second, you need to understand and have some experience working with data in table and lists. That is, you need to understand that in a table, a given column contains data of the same type, and that rows contain one or more columns, and that in lists, all of the data is the same type. Third, you need to have some basic math and statistics knowledge. The statistics need not be much more than summation, means, median, maximum, and minimum, but I am assuming at least this level of knowledge. Likewise, nothing more than basic algebra math skills are assumed. And finally, and most importantly, you need to have a curious mind and be enthusiastic. This is a course about seeking understanding through data. You will learn with a little manipulation you can create models that can predict the future, but getting there will take a little bit of effort. I'm going to assume that if you've made it this far, it's because you have an interest in machine learning. But just in case you have some doubts, let's talk about why you want to watch the rest of the course. One obvious reason for taking this course would be to add a skill set, namely machine learning. As developers, we always want to constantly add skills and learn how to do things in new and interesting ways. And just like when you learned a new programming language, you need a set of resources, like this course, to get you started. This course is about machine learning, and machine learning is one of the key technologies used in the broader field of data science. And as we see, data science itself is a blend of math and statistics, software development, and expertise in the problem's subject area. Machine learning is one of the most important parts of data science, and is at the intersection of software development and math and statistics. I know you have the software development expertise, so in this course we'll blend that with using math and statistical algorithms and models. And if you add some subject matter expertise, you can become a tech unicorn. One of the things that has made data science so exciting now is the recognition of what machine learning can do for companies. In particular, the ability to predict outcomes can directly impact a company's bottom line by defining new business opportunities and bringing in new customers. And with this new awareness has been a substantial increase in the salaries of data science professionals, especially for tech unicorns. In fact, Forbes recently had this quote, "But beyond the financial gains, I hope this course can satisfy your curiosity about machine learning and how it is applied. Once you understand the basics of machine learning, who knows where your skills will take you? Perhaps this will be your next project? If so, I for one welcome our new robot overlords." You now have a high-level understanding of machine learning and how it uses data instead of explicit program logic to determine how to solve a prediction problem. Next, we have a quick introduction to Python and Jupyter Notebook. If you are familiar with Python and Jupyter Notebook, feel free to skip this information and head over to the next module on the machine learning workflow. If you've been around programming for any length of time, you've no doubt heard about Python. Python is an easy-to-learn language, sometimes used as the first language to teach programming. It has clear and powerful object-oriented features. It uses a structure based on indentation that makes programs easy to read. And most importantly for us, comes with standard libraries that support many common programming tasks, including machine learning. Right now there are two versions of Python, 2.7 and 3.x, commonly in use. Python 3 came out in 2010 and is the future of the language going forward. However, there are some incompatibilities with Python 2.7. Python 2.7 is the last version of the Python 2 family and has been largely static since 2012. Many people still use 2.7 because their code has syntax or library dependencies on Python 2. At this time, most of the major libraries support Python 3, and Python 3 is a recommended version of the language. In this course, we use Python 3. More specifically, we use Python 3.5 and the appropriate Python 3 version of the libraries. Speaking of libraries, for machine learning, the libraries we are most interested in are NumPy, which supports scientific computing through n-dimension arrays, has linear algebra support, and many other numeric capabilities. Pandas, which provides data frames that make it easy to access and analyze the data. We use these data frames to hold and manipulate our data. Matplotlib, which is a 2D plotting library which produces publication-quality graphics on our data. During the course, we will use several plots to help us understand the data. And finally, scikit-learn, which provides simple and effective tools for performing many of our machine learning operations. This includes implementing the algorithms we train into predictive models, methods that make it easy to pre-process data, methods that assist in the evaluation and comparison of model performance, and support for many more machine learning tasks. We will use all the libraries and a few more, but as you might expect, scikit-learn is the library we will use the most. Of course, as developers, we know that the language is just part of the story. The development environment and associated tools are just as important. For these, we use Jupyter Notebook, which was previously called Python Notebook. The Jupyter Notebook environment creates a single interactive document containing text, graphics, and code. This is a great environment for the iterative trial and error nature in which machine learning solutions are built. As we will see, the result documents are presentation quality, and these documents can be shared and worked upon by multiple users. The notebook now supports over 40 languages via kernels, which are language plugins. Languages supported include Python 2.7 and 3.x, Ruby, R, Haskell, C#, PHP, Scala, and many others. Now let's get everything installed. There are numerous ways to get Python and Jupyter Notebook set up on your system, but the way I suggest is to use the Anaconda distribution. This distribution of Python will install Python, Jupyter Notebook, and all the applicable libraries all at once. To get the installer, go to the listed URL and select the installation of Python for your system. I strongly recommend you select the installer for the latest 3.x version of Python unless you need an older version of Python for some reason. And if you do need to support multiple versions, check out creating Python version-specific environments with the Conda Package and Environment Manager. These environments can make supporting Python 2.7 and 3 side by side pretty painless. Next, we'll see Jupyter Notebook and Python in action. Now let's see a quick demo of Jupyter Notebook in Python 3.5. To launch Jupyter Notebook, you need to start a new shell window. Do not close this window until you have completed your editing session, since the Jupyter web server will be running in this shell. Once the window comes up, we launch Jupyter Notebook by going to the command line and entering Jupyter Notebook. As you see, this launches a web server that will start in the current folder. You should also see a new browser window with the Jupyter file browser appearing. It will start from the folder that was current when you launched the notebook. Navigate to wherever you want to create your notebook. If you need to create a folder, select the new drop-down and select Folder. The folder will be created with the name Untitled Folder. You can select this folder and then rename it. Once you get to the folder where you want to create your notebook, go to the New drop-down and select Python 3 to create a new notebook associated with the Python 3 kernel. Congratulations! You just created a new notebook. Notice that the title of the notebook is untitled. Let's change the title by clicking on it and entering a new title in the dialog. Now let's review the interface, which may look a little strange at first. We see a single cell displayed into which we can type code. What you type in depends on the cell type. By default, new cells are for entering code. Let's change this cell type to Markdown so that we can type in a title and description of the notebook. We can change the cell type to Markdown by using the drop-down box or by pressing Escape M. In a similar manner, you can change the cell type to code by using the drop-down or by pressing Escape Y. As we see, Markdown denotes a header by a line that starts with one or more hash signs followed by a space. The level of the header is determined by the number of hash signs. A level 1 header is the most major and is denoted by 1 hash sign. A level 2 has 2 hash signs, etc. The levels are similar to the H1, H2, H3 you have seen in HTML. The second line is plain text except for Jupyter and Python 3, which have asterisks denoting emphasis. Like headers, if you put 1 asterisk, you get level 1 of emphasis. 2 asterisks cause level 2 emphasis, etc. But right now, the cell contains raw Markdown text and it looks pretty ugly. That is because we have not processed the Markdown yet. We process it by pressing Shift-Enter anywhere in the box. And look at the difference. The Markdown has been processed to produce nicely formatted text. There are a lot of Markdown commands you can use, and if you do a web search, you'll find a number of great Markdown tutorials. Now let's try some code. Of course, our first code example has to be some variant of Hello World. Let's create a cell with the header for this Hello World example. Again, we need to ensure it is a markdown cell. And since it is a header for this example, we'll enter a level 2 header. What should I type? Correct, I should enter 2 hash signs and a space for a level 2 header. Now we enter some code below this title. Let's do a classic Hello World with a little twist. Here we will see string concatenation in action. The editor has completion, so if I type in my and hit tab, it looks up the variables and automatically completes a variable as my name. We are now ready to print our string, but I know the syntax for the print statement changed between versions 2 and 3, and I'm not quite sure which syntax I should use. No problem. I type print and press Shift-Tab. It shows the documentation for the print statement. I see that print is now a function, so that I need to put my text and variables in between parentheses. But what is that end argument about? I press Shift-Tab twice and see the end argument lets us define a character to append, like new line to the end of the line. Notice that there are 2 types of arguments used in Python. Value is a position-based argument that is the first argument to the function. There are also keyword arguments such as in, for which the caller must specify the keyword followed by an equal sign. Also notice that the keyword end has a default value of \n, which is a new line character. If we wanted a blank line after our print statement, what character string would we pass? That's right, we would pass \n to get 2 new line characters after the text, one to end the current line and one to create a blank line. Now that we know the parameters, let's complete the print statement. I type in HEL and hit tab. We now see there are 2 items starting with HEL, the command help and the variable hello statement. I select hello statement and press return. Then enter the parameter end and press tab. To be correct syntax, an equal sign is needed, so it's added automatically. Then we move to the next cell and nothing happens. What is going on? Oh, silly me, I forgot to press Shift Return to tell Jupyter Notebook to execute the contents of the cell. Once I do this, the contents of the cell are executed, and we see Hello Jerry followed by a blank line. That's great. Let's try another example. Let's try a loop. First we add a description. Oops, all that red means I started typing text into a code cell. No problem, we can just change the cell type to Markdown, and then press Shift-Enter to process a Markdown. Much better. And then let's enter in a for statement. And below that we enter in the operations we want to perform within the loop. Notice that the operations in the loop are indented further than the for statement. This indentation is how Python knows that the code belongs in the loop. There are no curly braces or other characters that define the enclosing structure of code in Python. Indentation defines parentage and makes the code very easy to read. Also notice that by default the print statement supports format strings where all occurrences of that curly brace 0 and curly brace 1 get replaced by the first and second arguments in the format function. Now let's run the loop by pressing Shift Return. Uh-oh, syntax error. Looks like I forgot to define x. I'll define it in the first code cell to make the second code cell look neater. Then we rerun the loop by entering Shift-Enter. What? It's still broken. What's going on? This shows one of the basic features of the Jupyter Notebook. Namely, only the code in the cell that is current is executed when you press Shift-Enter in that cell. When I entered x10, I forgot to do this, so x is undefined. If I go back to the first cell and press Shift-Enter, it reruns the contents of that cell. Then I can go to the loop cell and everything works as expected. The need to press Shift-Enter in both cells is both good and bad. On the one hand, it means that you can make a change to a cell and only evaluate the cells where you explicitly enter Shift-Enter. On the other hand, it means that if you change something, the cells below will not see the change until you rerun them. As you can imagine, this can be a frustrating bug to find, especially when you've made a number of changes in different cells. To get around this, you can just rerun the entire notebook. Go to the menu item Kernel, Restart and Run All option. This will rerun all the cells in your notebook from top to bottom. And now our loop works. Okay, now that the loop is running, let's take a look at the output. As you see, the loop now prints out the expected numbers. That is, those are the expected values if you're already a Python programmer. Developers coming from other languages would likely have expected the range to return 1, 2, 3, 4, and 5, not just 1, 2, 3, 4. This is a feature of Python looping. In Python, you specify the starting point and the value not to exceed, not the ending value. Well, surprisingly, in these few examples, we've gone over enough to get us started. So we can press the Save button to save our work, and everything is written to a file with the notebook name plus an extension of IPYNB. So in our case, the file name is pythonfirststeps.ipynb. The IPYNB extension comes from the old name for Jupyter Notebook, IPython Notebook. Now that you know how to use the notebook, we can head off to the next module where we'll go over the machine learning workflow. See you there! Building a machine learning solution is a complex set of tasks. Over the years, a machine learning workflow has been developed to organize these tasks in an efficient manner and ensure that no critical steps are missed. In this module, you will get an overview of various tasks that comprise the machine learning workflow and tips on how to best use the workflow. But first, let's define the machine learning workflow. While there are numerous definitions to the machine learning workflow, I like this definition. As you can see, the machine learning workflow is orchestrated and repeatable. This means work has been purposely organized into defined tasks, and the same workflow can be used to develop solutions to different problems. Transforms and processes information. That is, before we can use data in creating solutions, it must be transformed into a format we can use for processing. And finally, the product of the workflow is a prediction solution. Implicit in this is the prediction solution must meet the performance criteria we specify. With this definition in mind, let's take a look at the steps in the machine learning workflow. Our first step is to define the question we want the solution to answer. We need to define this question in a way that guides the remaining steps in the correct direction. This requires thinking carefully about the goals we want to achieve, the data we need, and the processing we can perform. Once the question is defined, we can gather the data we need to answer the question. This can be tricky because data are often incomplete, inaccurate, and conflicting. When we have the question defined and the data we need, we can consider which algorithm to use. This is not an easy task as there are many algorithms available, but if we have properly defined the question will help us select the proper algorithm. Once we have the algorithm selected, we need to use a subset of the data we have to train the algorithm. This training process will result in creating a trained model that predicts results on similar data. Once we have a trained model, we need to test its accuracy on new data that was not used to train the model. This testing will generate statistics with which we can determine if the model will meet our requirements or needs to be refined. If refinement is needed, it may be necessary to go back into the workflow and alter or get more data, change algorithms, adjust training parameters, and sometimes some combination of all three. When using the machine learning workflow, there are some important things to keep in mind. First, there is an inherent hierarchy of these steps, with the earliest steps being the most important since the latter steps are dependent upon them. That is, you need to correctly define the question for which you are creating a solution. Then you have to get correct data which will allow you to train your algorithm to come up with a prediction. Only when you have the model trained can you evaluate its accuracy. When moving through the workflow, it's not unusual to have to return to a previous step. For example, as you work with data, it may be apparent that you are asking the question incorrectly. And regarding data that you find will almost never be in the format that you need. Expect to spend a considerable amount of time locating and transforming the data into the structure that you can use. Also, within reason, more data is usually better. Remember, the mathematical equations needed to model your data may be complex with strange quirks. The more corner cases you can cover with the data, the better the model will be trained, and the more accurate your resulting predictions will be. Finally, try not to push a bad solution. It's easy to fall into the trap of thinking with just a few more tweaks, the stars will align and your model will start performing correctly. If you find yourself in this situation, it's better to take a step back and ask yourself, do I have the right data? Do I need to pre-process data? Or do I even have enough information to continue? Now that we have seen the structure of the machine learning workflow, let's see how we can apply it and use the workflow to build a solution that will predict whether a person will develop diabetes. As with any software project, having a clear definition of what we want the machine learning solution to achieve is critical. In this module, we'll go through the first step in the machine learning workflow, asking the right question. We'll convert our general goal of predicting if a person will develop diabetes into a solution statement that can be used to guide our work. At first glance, it might seem that asking the right question is easy. After all, don't we already know that we want to predict if a person will develop diabetes? But this is a case of appearances being deceiving. We need a question that will direct and validate our work. That is, the question which drives the direction of the data we gather, how we mold the data, how we interpret the solution, and the criteria we use to validate the solution. What we need is more than a simple one-line question. Rather, we need a solution statement defining the end goal, starting point, and how we achieve the end goal. Let's state the goals for our solution statement. The final solution statement should define the scope of the solution, including data sources, define target performance measurements for the solution, determine the context for using the solution, and define how the solution will be created. Let's start adding these requirements and see how they impact the solution statement. We will use our original goal of predicting if a person will develop diabetes as the starting point. Based on the needs of the solution, we can see if there are some assumptions that can help with the definition of the scope of the solution. A review of the data on the American Diabetes website shows that diabetes has several factors that can help guide us. These are age, older people are more likely to get diabetes, and race. Certain racial groups, including African Americans, American Indians, and Asian Americans, are more likely to have diabetes. Interestingly, gender does not seem to be a factor. Of these factors, race stands out as something we may be able to use as a selector. Specifically, we can see if we can select data from one or more of the higher diabetes risk racial groups. With the race feature, we can do a preliminary evaluation of data sources. There are several sources of data on diabetes, but one stands out as the best data source for our purposes. That is the Pima Indian Diabetes Study, available at the UCI Machine Learning Repository. This is a study of diabetes in women in the Pima Indian population located in the Phoenix, Arizona area. The study was conducted in the 90s and is a classic data set. When we incorporate the use of the Pima Indian data set, the statement changes to, using Pima Indian diabetes data, predict which people will develop diabetes. One important aspect in any prediction algorithm is how accurate it is. So for our prediction, what prediction accuracy should we reasonably expect? We are defining the evaluation in a binary fashion, diabetes or not diabetes, and we want to be as accurate as is reasonable. Historically, disease predictions are notoriously bad. This is due to many factors, but the biggest is that we are all genetically different. Even people that are genetically identical at birth, identical twins, experience different factors during their lives such as lifestyle, environmental exposure, and sickness that lead to different health results. Against this backdrop, 70% accuracy is a reasonable goal, so let's use that as the bottom of the acceptable range. This changes the statement to, using Pima Indian data, predict with 70% or greater accuracy which people will develop diabetes. The context in which the prediction will be used needs to be considered, since this can drive decisions on data to capture and mold. For example, we are predicting disease. What does it mean to predict disease? Does it mean we are absolutely sure about the prediction? What are the common practices in the field of medical research? In medical research, we see that there are many variables in each individual, and many of these are unknown with respect to how they affect the probability of developing a disease. As we discussed earlier, even identical twins with the exact same DNA show variance. So in medical research, what is predicted is the likelihood of developing a disease. Let's incorporate this likelihood estimate into the statement. The statement is now, using Pima Indian data, predict with 70% or greater accuracy which people are likely to develop diabetes. It is always useful to put down on paper how you're going to approach the problem. With machine learning, I like to put down the general steps. For our solution, these are: use the workflow, process the Pima Indian diabetes data, transform data as required. This changes our solution statement quite a bit. The statement is now, use the machine learning workflow to process and transform Pima Indian data to create a prediction model. This model must predict which people are likely to develop diabetes with 70% or greater accuracy. We now have the final solution statement. This statement defines the data we will use, the performance expected, and even how we will go about creating the solution. Join me in the next module, where we will see how we can use the machine learning workflow to implement the solution we have defined. In the previous module, we worked through the first step of the machine learning workflow, asking the right question. In that module, we developed a solution statement for our prediction. In this module, we will use that solution statement to guide us in getting and preparing data. As you know, machine learning is based on data, so it should come as no surprise that getting and preparing data is a major step in the machine learning workflow. And just like preparing a surface before painting, good data preparation can make the task of creating a well-trained model much easier. Likewise, poor preparation can make the task painful and full of corrective and redo work. With this in mind, let's take a look at what we will do in this module to get and prepare our data. We will start by discussing the data we need. Once we have the data, we need to load it into Python and inspect and clean the data. We also explore the data to understand its structure and make any necessary alterations. Finally, we mold the data into tidy data, which works best with machine learning algorithms. We will do all this work in Python, running inside Jupyter Notebook. But right now, you may be asking yourself, what is this tidy data that we are trying to produce? Here is the definition of tidy data. If you have any SQL experience, as you read through this definition, it may strike you as very familiar. In fact, tidy data has attributes of what we try to achieve in database normalization. We want each variable to be a column, each row a unique observation, and we store them in a table, which is in code's third normal format. But tidy data is a bit more pragmatic than normal forms, and focuses on presenting data in a clean, readable format versus underlying structures like keys. I like to think the data is tidy when it looks like it was produced by a well-designed view, and getting our data to a tidy form can take a little time. In the literature, you'll find estimates of 50 to 80% of the time in a machine learning project is spent getting, cleaning, and organizing data. At first, I didn't believe this, but experience has taught me that these numbers are accurate. Why is this? Today, we are swimming in seas of data, but even with all that data, the data we need may be difficult to find. So where can we look? Google, obviously, but be careful. Not surprisingly, quality varies wildly. Be extra careful when looking for data on controversial topics like global warming, vaccine side effects, etc. Fake, unvalidated data abounds online. Government sources are often good. There's usually lots of data and it's peer-reviewed, and the data comes with good documentation on the meaning of the data, that is, metadata. Professional groups and companies can be a good source of data also. Professional societies provide datasets. Twitter provides access to tweets, and lots of analysis has been done on tweets to determine the tenor of them. Financial data can be retrieved from free APIs from companies like Yahoo. If you work in a company, your own IT department can be a good source of company-specific data. Similarly, your department likely maintains department-specific data, and sometimes it's just all of the above. A lot of the time you need data from many sources, and you have to weave them together into tidy data. With these sources in mind, let's see where we can get the data we need to solve our problem of predicting diabetes. When it comes to getting data, we're lucky. The large UCI machine learning repository has a version of the data we need in its Pima Indian diabetes dataset. However, the Pima Indian diabetes data from the repository is too perfect. It does not have many of the issues you will find with the data you encounter in real-world situations. Because of this, we will use a slightly modified version of the data from the repository that is provided in the demo file pima-data.csv. The data in the CSV file is from female patients at least 21 years old. There are 768 patient observation rows, and each row contains 10 columns. 9 of these columns are feature columns, such as number of pregnancies, glucose concentration, and insulin levels. One column contains the class, diabetes, which has the value of either true or false. Using this data, we will be able to predict how likely it is that a person will develop diabetes. The data in the CSV is not perfect, and as such will illustrate data rule number 1. The closer the data is to what you are predicting, the better. This may sound obvious, but it's true. Having a single field saying this patient has diabetes or not is great. In a lot of cases, you don't have what you are trying to predict so clearly defined in the source data. Rather, you have to infer it by combining columns from multiple sources, and each combination brings up a potential area of misinterpretation or otherwise coming to the wrong conclusion. But no matter how good the data appears at first glance, it will almost never be quite what we need, or better stated, data rule number 2, data will never be in the format you need. If you have done any data processing, you know how true this is. You will always have to do something to the data to reformat it. In Python, we will utilize Pandas data frames to make this reformatting easier. Pandas data frames appear as a table with a column for each feature in the class, and a row containing the observation of these features in the class for each patient. As previously mentioned, the demos in this course utilize a modified version of the Pima Indian data. To get you started, I have created a GitHub repository with this modified version of the Pima Indian CSV data file and the notebooks used in this course. You can find the repository at this URL. When you get to the GitHub repository, you should see a screen similar to this one. If you're familiar with GitHub, you can clone the repository using this URL. If you're not familiar with GitHub, you can get the repository by pressing this button to download the zip version of the repository. All of the notebooks are in the Notebooks folder. Also in the Notebooks folder is a subfolder named Data that contains the file pima-data.csv, which is the modified version of the Pima Indian diabetes data. In this demo, we will go over loading our version of the Pima Indian diabetes data, exploring that data to see what sort of information it provides, and cleaning the data of extraneous fields that might cause us difficulties in utilizing the data. Prior to beginning this demo, I placed the CSV file containing our version of the Pima Indian data into a folder named Data. Let's go into Jupyter Notebook and start looking at our version of the Pima Indian diabetes data. At the command prompt, we enter the command Jupyter Notebook to launch the notebook server. We create a new notebook by selecting the Python 3 kernel. And we change the name of the notebook to something useful, Pima Prediction. We change the first cell to a markdown cell and enter the top-level header for the notebook. And then we add a header for the import statements. We need to import some basic libraries. Pandas provides data frames, Matplotlib provides plotting support, and NumPy provides scientific computing with n-dimensional object support. Finally, we add this Jupyter Notebook magic function that causes plots to be displayed inline instead of in a separate window. We are now ready to load our Pima data into the Pandas data frame. We use the Pandas readCSV function. By default, this function assumes that the first row of the CSV file contains the column headers. Let's check the structure of the data by using the shape function. The shape function displays data in the format number of rows, comma, number of columns. So we have 768 rows with 10 columns. Let's inspect the newly loaded data. We use the head method to see the beginning rows of the data frame. Passing 5 as the argument tells the method how many lines to return. Likewise, we use the tail function to see the end of the data frame. Notice that each row has a zero-based index. Also notice that the Pandas data frame has column names. We use these names to access specific columns. We can also use these column names with a row indice to access the value in a specific column in a specific row. These columns represent logical features in the results in the data. So often you hear the term feature and column used interchangeably, but they are different. A feature is something that's used to determine a result. A column is a physical structure that stores the value of a feature or result. We will need to refer to the definition of the columns from time to time. To ensure the definitions are available, let's add a feature definition table to our notebook. In general, we want to eliminate any column that we do not need. In particular, we want to eliminate columns that don't have any values or are full of empty values. But we also want to eliminate columns that are duplicates or provide the same information in a different format. We could visually inspect columns to see if they really are the same, but visual inspection is error-prone and does not deal with the critical issue of correlated columns. Correlated columns state the same information in a different way, such as an ID and the text value for the ID. These correlated columns do not add any information about how the data causes changes in the result, and worse, they can amplify a bias because some algorithms naively treat every column as being independent and just as important. For example, imagine what would happen if we were predicting house prices and had the size of the house in both square feet and square meters. Size could result in being twice as important as it should. Pandas makes it easy to see if there are any null values in the data frame. The isNull method will check each value in the data frame for null values, and then the any method will return true if any nulls are found. Great, looks like we don't have any nulls. But how about those correlated values? To make it easier to visualize correlations, let's use the matplot library and create a function that cross-plots features so that we can see when they are correlated. The colors in this cross-plot run from blue, meaning not very well correlated, to dark red, meaning very positively correlated. Now let's invoke the correlation crossplot. Notice the column names running across the horizontal and vertical axes. This is a matrix showing which columns have data values that are correlated with values in other columns. Dark red means the columns are highly positively correlated. Since we have the same columns along the horizontal and vertical axes, we expect red squares on a diagonal from the upper left to the lower right, since this is comparing a feature with itself. But what about the red squares for skin and thickness? This means a strong correlation between these two columns. Let's check the correlation numbers to verify the results shown in the graph and see just how correlated the skin and thickness columns are. Notice the 1.00 running down the diagonal of the table. Again, this is because we are seeing the correlation of each column with itself, which is, of course, a perfect correlation. But also notice the 1.0 correlation between the thickness column and skin row, and the skin column and the thickness row. This means that the columns are changing in value in lockstep and in exact proportions to one another. Having two features that move together adds no additional information. We can either make note of this and make sure we try to avoid using both columns at the same time, or we can drop one of them. I'm going to drop the skin column. By the way, the skin column was created by converting the thickness, which was in millimeters, to inches. Let's look at the head of the data frame again. Look at this data and tell me if you can see the one-to-one correlation between thickness and skin. Maybe, but it's pretty easy to miss something like this, and one reason we use features like Pandas' core function to make the relationship obvious, and plotting the correlation in color makes the relationship hard to ignore. Now that we found the extraneous correlated columns, let's use the del command to delete the skin column. We can verify that the column was dropped by checking the head again. The skin column is now gone. Let's take another look at the plot to verify that there are no other correlated columns. The correlations look good. There appear to be no other correlated columns. Now we can move on to molding the data. We have done some good cleanup by removing some columns we did not need. Now we need to mold the data into data that we can use for training. This involves ensuring that the data types of the columns are what we need, and if required, creating new columns based on existing data. Let's now mold the data. Let's start by inspecting the data to see if there are any issues. Algorithms are largely mathematical models. As such, they work best with numeric quantities, and in fact, some algorithms require that all the features and classification results be numerical. We still have categorical results, Boolean true and false, for the diabetes feature. We need to change these booleans to integers to ensure they'll work with all algorithms. Specifically, we need to change true to 1 and false to 0. We do this with the Pandas data frame map method. We first need to define a mapping dictionary that defines true as 1 and false as 0. Then we use the map method to change the values from true and false to 1 and 0. Note that the Pandas data frame did all the work of iterating through the data. We didn't have to write any sort of loop iteration code. Pandas makes dealing with huge tables of data very simple and fast. Now let's check the data frame again with the head function. And we see now that the diabetes class is all 1 and 0. Reviewing the data, it looks like we have it in a form that we can use. We are just about ready to use this data to train the algorithm. However, before we use this data for training a prediction, we need to ensure the distribution of the data will allow us to train a prediction. This is driven by data rule number 3. Accurately predicting rare events is difficult. The basic issue with a rare event is it's rare. So the probability of you having them in your data is low, and the probability of accurately training the algorithm is also low. We only need a few percentage of the event to be able to train, but more is better. To ensure that we have a reasonable chance of correctly predicting if a person is likely to develop diabetes, let's check our newly cleaned data. Let's check the number of true and false diabetes cases. Pandas will let us easily search through the columns by name and see how many times diabetes is true, 1, and how many times it is false, 0. We can then calculate the percentage of the time the diabetes class is true and the percentage of the time the diabetes class is false. We have about 35% diabetes, which means we can reasonably train our prediction model using the data we have. If the vast majority of the data were either true or false, the standard learning techniques we will apply might not work very well. In cases where we are trying to predict something that did not happen very often, we need to use special techniques, which are beyond the scope of this course. But with 35% true and 65% false, standard prediction techniques can be used. So congratulations, we have our training data. But does anybody remember what we did to get here? This brings up data rule number 4, track how you manipulate data. A lot of manipulation of data that you do in machine learning is trial and error. When you manipulate the data, it's very easy to change the meaning of the data. This can be done intentionally, but it can also be done unintentionally. By keeping track of manipulations of the data, you can always reproduce your data at any step and see where you went wrong. Since we are using Jupyter Notebook, keeping track of our changes is done for us automatically. We have the best of both worlds. We have the interactivity of the Python interpreter with tracking via code cells, plus markup cells where we can enter detailed code descriptions and links to reference sites. Additionally, like all coding, we need to ensure that we use some sort of source control to track changes and allow us to restore things that we might accidentally delete or alter. Let's summarize how we prepared our data. First, we loaded the diabetes data from our CSV file into a Pandas data frame. We used a function to visually identify correlated features. From there, we cleaned the data by removing the extraneous column of the correlated features. Then we molded the data by changing the data types of columns into what we needed. We also verified that we had enough true and false values to use the data for prediction. And along the way, we discussed data rules that guided our work. Join me in the next module, where we'll select the algorithm that we will train with our data.